Welcome to this explainer on three-phase transformers. Today, we're bridging the gap between those massive physical hunks of steel you see out on the grid and the critical, almost hidden vector group codes that literally prevent catastrophic grid failures. Let's jump right into the anatomy of our electrical grid. You know, theoretically, you could build a three-phase transformer bank just by wiring together three separate single-phase units. But in the real world, utilities almost never do that. And the reason is actually pretty simple. Merging them into one single three-phase core saves a massive amount of physical footprint and, well, literal tons of steel. It's basically the ultimate exercise in construction efficiency. So, let's start with the raw materials, specifically looking at core form construction. Just imagine a simple, rectangular, laminated piece of steel. The transformer windings are wrapped directly around the vertical legs of this loop. It's a brilliant way to illustrate how a single structure efficiently shares magnetic flux across all the phases. Plus, it keeps everything super compact and way easier to cool down. But there's a really fascinating split in design philosophies here. While that core type completely dominates standard distribution and mid-sized transformers, because honestly it's just simpler to build, the shell type flips the script entirely. In a shell-type design, the core surrounds the windings on all sides. It completely encloses them, almost like a protective shell. This gives you superior mechanical bracing and the absolute maximum short-circuit strength required to withstand the violent physical forces inside those massive critical grid units. Okay, let's zoom in on the copper wiring itself. When connecting these three phases, engineers essentially have two main choices. First, you've got the star, or Y connection, which connects all three windings to a common neutral point. This is fantastic because it gives you a usable neutral for grounding, which lets you serve single-phase loads easily. On the other hand, you have the delta connection, which forms a closed triangle. Now, it has no neutral, but it handles unbalanced loads so much more gracefully. And crucially, it traps those unwanted internal triplet harmonics right inside that closed loop, instead of letting them leak out onto the main power line. Now, these crucial copper configurations aren't just hidden away inside the transformer tank. They're explicitly encoded into a compact little vector group license plate, something like Dyn11. So the trick here is knowing exactly how to read this code. The capital D tells us the primary winding is delta. The lowercase y means the secondary is star. And that little n, that signifies that the neutral point from the star secondary is physically brought out for us to use. And then, of course, there's that number at the end. That 11 isn't just decoration, it's actually a clock position. When you multiply that clock position by 30 degrees, it tells you exactly the phase relationship between your primary and secondary voltages. So 11 times 30 means the secondary voltage lags the primary voltage by exactly 330 degrees. Pretty cool, right? So let's try a high-stakes application question. If two different transformers both use delta and star windings, can you safely parallel a Dy11 transformer directly with a YNd11 transformer to share a heavy grid load? Just take a quick second to think about what we literally just learned regarding those clock numbers. The answer is a hard no. Absolutely not. Even though they both have delta and star windings, their vector groups are different, which means their phase shifts are entirely different. If you try paralleling transformers with mismatched phase angles, it drives a massive, destructive circulating current right between the two units. We're talking about forces that can completely destroy both transformers in a really spectacular fashion. Vector group matching is absolutely a hard rule. It is definitely not a polite suggestion. And you know, it's not just the phase angle you have to worry about. Matching the phase sequence is just as critical. Imagine your generator is pushing phases A, B, C, but the grid is expecting B, A, C. Even if your voltage and frequency are a perfect match, closing a breaker on a reversed sequence effectively swaps the phases and triggers the exact same type of explosive, catastrophic failure as a mismatched vector group. So, what should you really take away from this explainer? It's how all these different pieces just interlock perfectly. The physical steel core determines your overall strength and footprint. The copper, star, and delta connections dictate your grounding and harmonic handling. And finally, the exact math of those vector groups sets the hard, unforgiving rules of grid safety. You simply cannot mix and match without doing the math first. All right, so we've mastered the configuration codes and the physical layouts. But here's a thought to leave you with. What happens when the power running through that transformer isn't a clean, perfect sine wave? How do we calculate if that transformer can actually survive the massive heat generated by a harmonic-rich, nonlinear load? And exactly how does per unit impedance let us compare massively different transformers on equal footing? In part 2 of this explainer, we'll dive straight into the fascinating world of K-factor and per unit impedance to answer exactly that. Catch you next time.